So अब ऑन होगी ये.
Yes, sir.
So there is a force on this person, and that force is the Coulombic force, and the force is q small q divided by 4 pi epsilon naught r, and r can be really any distance, yeah, in the field. Right here, beyond the point P, the field vanishes. Okay, so there is a Coulombic force on the person. Okay, now this Coulombic force, and this really an opposite force the person has to apply, and that force is suppose Fzk. Okay, and that force is really the same amount of force but with the negative sign of F Coulombic. So the force which I will apply is this. It has to be the same amount of force, the Coulombic force. If I neglect every other resistance in my path, if I neglect the gravitational force, if I neglect other frictional forces and many other things, or the wind pressure and many other, so say this charge and I are really in the free space. So then the force Gk will just be a negative sign of Coulombic force. And from this Coulombic force, if I try to find out the intensity, if Coulombic divided by Q, the Coulombic force over this positive charge, small positive charge which is in my pocket, is equal to electric field intensity, which will be equals to capital Q divided by 4 pi epsilon naught r square. And r can be really any distance. R can be really any distance. Can be any distance from the center of the capital Q, from the center of capital Q positive charge, right? So this is the electric field intensity on the person. Now, whenever I try to find the potential difference or the work, uh, so the work which I do will be equals to minus the Coulombic work which the Coulomb fields, or the which the electric field is doing. So two words, and remember, uh, you normally talk for the work. You normally work is a scalar quantity, but the work done, the convention work done on positive charge, right? By positive charge, by field of positive charge is positive. Okay, and work done work done on positive charge by 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 me, right, in presence of positive charge is negative. Okay, so this is just a convention we are following. Okay, uh, in presence of positive charge, capital Q, okay, is negative. This is just a convention we are following. Okay, now remember, say this point is A. Say this point is P. Okay, and, and as we move through R, R any point, this one or this one or this one or somewhere here. Any point, suppose B. Any point is suppose B, right? Okay. So any point is B. Okay. Anywhere. So say you are measuring things here, so you take this as a point B. If you are measuring things here, so you take this point B. Why? Because point is fixed. So if you try to find the potential difference VAB, okay, it would be the potential difference of VA minus V. Okay. So really, we can really calculate these potential differences. Okay. So so work. If I count on this work, the Coulombic work, W Coulomb is equal to 4. The differential Coulomb, the differential work is the differential R, right? And if I try to calculate the whole work, I need to take the integral F dot R, and I need to take this integral on the path. Okay, so this will really be equal to charge into electric field intensity, charge to electric field intensity, the small charge into electric field intensity dot dr. Okay, so if I bring this to a new page, the work the work W will be equal to small q path integral electric field dot dr. So this is really my equation for the work. Okay, so if path is suppose it's q, path is from A to B. Okay, say B is some point here, right? B is point here. Okay, so here is VB and here is VA. Okay, right? So say B is a finite point. So you move from A to B or B to A. So you really move from B to A, A to B. Okay, this is the work done from A to B. A to B is the work. Work in this direction is the field work. Work in the other direction is your work. Okay, so from A to B, uh, E dot dr. Okay. And this work Coulomb, sorry, the Coulombic work divided by small charge from A to B, E dot dr is equal to VAB, the potential difference. Okay, potential difference. Okay, and the work which I do, my work will really lead to a minus of the Coulombic work, right? And right, this will really be the integral, the reverse integral from B to A with the negative. See, if you flip the integral, you introduce a negative sign, E dot dr. It's just a negative work. And this will be equals to VBA or equals to uh, which equals to minus VAB. Okay. which equals to minus VA minus VB. Okay, so this is the work which I do, or it will result in a potential which is negative. Okay, so sometimes if you are going against the field, you are having the positive potential difference. If you are going if you are going in the direction of the field, you are going to get the positive potential difference. If you are going against the electric field, you are going to get the negative potential difference. The negative potential difference is really a difference which you actually create, or which is the result of work done by you. Okay, so that's a little convention you need to understand and you need to follow, right? So if I solve these equations, I will find out that v is nothing but, if I try to resolve, it's the charge divided by 4 pi epsilon naught r, right? uh, and really this could be 1 over uh, RA minus 1 over RB. Okay, so 1 over RB minus 1 over RA. Okay, so this is the potential difference you are looking. Now, if I come back here, and when things are out of the field, I take them infinity. Okay, beyond field of capital charge, we have infinity. So r tends to infinity beyond field of q charge. Okay, so if you put infinity in the equation, you end up on the absolute potential. Okay, so if one of the point is at infinity, you end up on the absolute potential definition. Okay, so now coming to the definition of the absolute potential. So last time we saw the potential difference. So we have two definitions now: potential difference, okay, in the field of capital Q. Okay, and the second thing is absolute potential. Absolute potential, in the absolute potential, the reference point is infinity. Okay, reference point is infinity. And then we also saw one more very interesting equation, and that is the potential difference. If you try to work out in a certain field, for example, the potential difference of this positive charge, its potential difference, its electric field is this much, right? So if you try to move something from here to here, okay, so you need to do some work. Okay, that work must be negative from B to A. Okay, it goes this way from B to A. Okay, so you have to do some work in that context. Okay, so when you do that work, the work is the potential difference is really nothing but this value of E dot dl, where dl is the path. Dl is our path, this path. Dl is this path, really. So you put everything as we did last time, and you come up with the definition, with the result, and the result is that the potential difference between those 2 points is this thing. Okay, B, A, B. Okay, so we calculated this last time. Then we went on extending this result and said, what if we change our path? What if we do not move like this, but we first move to this point, and then to this point, and then come back to this point? Then you try to find the total field, the total potential difference. Of course, the potential difference must stay the same, and the work in the three paths must result in the same work as you go from uh, this shortest path from point B to point A directly. The amount of work you will be doing will be the same as the work from here to here, then to here, and then to here. Okay, so that's the amount of work you are going to do in the uh, in the path. Okay, so then last time we went through calculating the work in every path, the work from here to here. And we said our initial path has coordinates xb and yb, and our final point coordinates are xb. So what's the potential difference? Uh, the potential difference in this path, the coordinates of the initial point are in the denominator and the coordinates of the final point are in the numerator. So this is the amount of work you're going to do. In the next path, in this path from xb to xa, in the denominator you get xb square and in the numerator you have xa square. So this is what we worked out last time. Okay, and then in this path again, coordinates of the initial point which is xa square, coordinates of the final point which is xa square plus ya square. Okay, any question here? If you add up all the three parts, the potential of this part one and then the part two and then the part three, if you add them together, you will get the potential difference of this part. Okay, so which proves that the work done is the conservative electric field is independent of the. Remember, electrostatic. This condition must be there. Electrostatic. Okay. So we said if one of your path of this equation is at infinity, okay, uh, if one of your path is at infinity, okay, so if you take one of the paths, say this one to infinity, which means you have the positive charge here, and this was the point P, and someone is out of the field. Okay, infinity, this is r tends to infinity, out of the field. Okay, so then rb tends to infinity, so then you have to put infinity here, q over this equation, and it will really you go through this little mathematics. It's really um, this was your point A. This is somewhere the point B. Point B is, this is really R, right? So R, here is RA, here it is RB, right? RB is infinity. So when you put the values in this integral, um, RB tends to infinity, eventually making this term equals to 0. So you get the absolute potential. So if a person is coming from out of the field, and he reach here, the person reach here with the same positive charge, now he will be feeling the absolute potential of this positive charge, the absolute potential, because now he was coming from infinity, and one of the reference point goes to 0. So one of the reference point goes to infinity, and 1 over infinity distance makes it 0. So the person will be feeling the absolute potential. So here is that's the definition of the absolute potential. So now 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 we have a case. This theory of the last lecture and this little definition here, we can transform it this way. Say we have this positive charge, Q. Suppose we have this negative charge here. Okay, and you know that there's an electric field here. Okay, now of course, if both the charges are in the field of each other, okay, say this is point A, this is point B, so you have potential difference VAB, okay, which is VA minus VB. So you have a potential difference. Okay, you have a potential difference. Uh, if, for example, you have a positive charge and you have another small positive charge, again, this is big positive charge, this is small positive charge, and someone say you have an electron here in between, again, you have a potential difference. Okay, again, you have potential difference, of course, right? But for for certain for certain case, say you have this positive charge, huge positive charge, and say this another positive charge, a small one. Okay, now this entire thing is some arrangement, and a person which is far away here, he can move any and say he reach here. This is the point P, where at this point the person starts feeling the field. Okay, this person has some charge in his pocket, again maybe positive, maybe negative. Now really at this point this person will face the sum of the two fields. One is the field which is coming from this charge, other is the field which is coming from this charge. So he will face two fields, and for the person really this entire thing will create absolute potential. Why absolute potential for this person? This entire arrangement will create because the person was coming from the infinity. But if this person is somewhere here, if the person is somewhere here, so when the person was here, he was feeling absolute potential. When the person was here, he was feeling absolute potential. But now when the person is here, this person will feel potential difference, or the charge which is in his pocket will feel the potential difference. Okay, but the person having some charge in his pocket will feel absolute potential if he is out of the field of those two positive charges. When he come to a point where the field of those two positive charges starts over, he will start feeling the absolute potential. Okay, so for this person, for all calculations, you consider the absolute potential of this entire arrangement or this structure or this uh, material having all the positive charges. But as soon as the charge enters into those two fields, now you will start defining the potential difference. So there may be an electron which is feeling uh, there might be an electron. Let me put a different color. There might be an electron. The electron will feel a potential difference. So again, if I try to create a new situation, say this is huge positive charge, this is huge negative charge, right? This is VA, this is VB. Then if say we have an electron in the pocket of a person, some person, right? This electron will feel, potential difference. Okay, so the electron will move, and we know the situation. The situation is that we have the electric field going from positive to negative, right? Uh, we have positive and negatives, and let me uh, let me show it more properly. Say we have huge positive charges, right? and say we have huge negative charge here. Now, if you have an electron here, which is, you know that the electron will always move against the electric field. This is the electric field. Electron will move against the electric field. So when the electron reach here, when the electron reach here, it will drop here and effectively making one positive charge, and so the charge will reduce. So electron and positive charge, the two combined together will make effectively a nothing value. Okay, will, so the electron will neutralize one of the positive charge, and because of that neutralization, the volt here Va will drop. Okay, so when say on another instant, another electron comes here and drops here, so it will neutralize another positive charge. Okay, let me remove them. They are there, positive negative charges are there, but they will neutralize each other. So the voltage will further drop, right? Is this clear? Any question here? So, so I hope the definition of the absolute potential is clear. Okay. Any question here? No question.
No question, sir. No question.
Okay. So, so absolute potentials are those potentials which are produced by one charge or one kind of charge distribution, or even if you say you have say in a certain place you have positive charge, but at the same time you have some negative charge also. So depending on the majority of positive charge or negative charge, the net charge is positive, because we have 5 positive, 3 negative, so the net charge is 3 positive. Okay. Okay, 3 positive. So when we have in a certain place, we have positive and negative combined together, or we have only positive there, or we have only negative there, we talk about the absolute potential. But when you have this kind of situation, that you have positive charge, you have negative charge, and say an electron is moving in between, then uh, in that situation you talk always for the potential difference. Okay, and how this potential difference is coming? This potential difference will come from VAB will come from negative of that electron from B to A in the field of E dot dl. Okay, B to A, because you are moving it from B to A. Okay, so we have then the negative potential. Okay, right? Any question here? This could be a complete electrode. This could be a complete electrode. Okay, cathode and anodes. An electrode having all the positive charges, and electrode having all the negative, probably one terminal of the battery, positive terminal of the battery, and negative terminal of the battery. Okay, so we start talking about the absolute potential. Any question here?
No,
Do you have any idea about the Van de Graaff?
No, sir.
Van de Graaff, let me show you. Okay, how can I share my browser here. Let me try. Do you see the browser?
नो सर, स्लाइड्स नजर आ रही हैं अभी तक।
Just like there are, एक minute. Do you see the browser now?
Yes, sir.
यस सर।
Now look here. Wendy. Wendy Graph was a person, right, who built this arrangement. Do you see now the Wendy Graph? Yeah. Do you see that Wendy Graph? It's an arrangement where you produce static charges on its surface. Okay, so you produce a lot of positive charge, suppose, on its surface. That's the Wendy graph. Wendy graph generator. Wendy graph was the person, the name of the person who first experimented this arrangement. Right? This was the Wendy graph. Have you seen this in the movies of Mr. Bean or in others? This arrangement, yeah. You see, this structure has lot of positive charge, and if you touch it, you feel like this girl, right? And so Wendy graph, this one,
Yes, yes, sir. We have seen this in Tom and Jerry.
yeah, you must have. Okay, now let consider this Wendy graph. So what was the equation of the absolute potential, by the way? V equals to Q over 4 pi epsilon naught R, right? And say, do you see now the PowerPoint presentation?
नो सर।
No? Do you still see that Explorer? Okay. Say this is our Wendy graph, okay? Okay. Say its radius is how much? R is say 0.3 meters, right? Its radius is 0.3 meters, right? And there's a huge positive charge on this Wendy graph, right? You know how to build this positive charge. There's a circuit behind it, and the circuit you just saw, in the circuit you just saw here. Look, this kind of circuit, which can charge this huge metallic sphere, right? So there's a circuit which can charge this one, and say you charge this one. So how much absolute potential at this point P? Vp is how much? So that a girl when touch this Wendy graph, this little girl when touch this Wendy graph, how much potential she will feel? How much voltage will flow through her body? Right? How much voltage will flow through her body? So how you will calculate that? Vp will be equals to Q over 4 pi epsilon naught R. Say Q is 10 microcoulomb. So 10 into 10 to the power minus 6 divided by 4 pi epsilon naught, R is 0.3. You can calculate. Okay. Any question here? Vp at R equals to 0.3. What will be the Vp at R equals to 0.6? 0.6 is somewhere here. This is 0.6. It would be Q over 4 pi epsilon naught 0.6. You can calculate. Vp you can calculate at 0.9. R equals to 0.9. You can calculate that. Q over 4 pi epsilon naught 0.9. You can calculate different locations, right? So when you touch, you can calculate, you can do many things, right? Any question here?
No question, sir.
No question? Now, can you observe that as we increase the charge on this Venn diagram, VP is proportional to charge. So if you raise the charge on the Venn graph, potential will raise. Is this okay? A point will come. A point will come when you have enough charge on this Venn graph, when you have enough charge on this Venn graph, and you have no more space for the charge, no more space for the charge. That will be the capacity of this Venn graph. Okay. So a point will come when this structure is fully saturated of charges, and then no more charge will be occupied here, and that will be the capacity of the Venn graph. Okay. So no more charge. What will happen then when that happens? Any idea? What will happen when that happens? Okay, so it's a question, right, for you. Okay, there must be some kind of constant in this equation, right?